welcome back. So today we're going to go over some super basic circuit theorems because we are going to go on and we're going to do some filters today. And filters, a passive filter, which means something that doesn't have any circuitry monitoring or controlling it. It just kind of sits there and does its thing. It doesn't need power, it doesn't need anything. They consist, that looks like this. Okay, so this is a basic filter. We're going to learn how you can make sense of this and just, without going into all the maths, intuitively look at that circuit and just immediately be able to tell what that's going to do. Okay, so to start off, before we go diving into looking at how capacitors work, we haven't really said much about resistors. So resistors are the most simple component that you can really get in electronics. Circuit symbol for a resistor is this. And we're going to just go over the three kind of most key circuit laws, theorems, whatever, that you need to know to be able to analyse a circuit, or at least have a rudimentary knowledge that they exist. The first one we've seen before, this is Ohm's law, V equals IR. So all that says is that if there's a current here flowing through a resistor, if we know two of these, if we know the voltage and the current, we can work out the resistance. Or if we know the voltage and the resistance, we can work out the current. Or if we know the current and the resistance, we can work out the voltage. And for DC circuits, which is what we're doing at the moment, that applies to any individual component. So if I had R1 and R2, we've got some current flowing through here. So this current flows through both of these because they're in series. So we could work out the voltage drop across either one of these by just multiplying the current by the resistance. Right, easy. Alright, so this is our second thing that we need to know. It's called KVL, Kirchoffs voltage law. And this symbol here is a sigma. Right, it looks like this. And it means the sum of. It's just a Greek letter, it's just like a shorthand mathematical notation. So the sum of all the voltage loops in a closed path has to equal 0. The sum of all the voltages, sorry, has to equal 0. So what that means in English is if we have a circuit, all the voltages in this loop have to add up to 0. So what we can basically do is we can think of that as we've got sources and we've got components. So sources are supplying your voltage, like your batteries, like your power supplies, and components have voltage dropped across them. So you take all of your sources, so we've got one, this is V, so we should call it V minus the voltage drop across this resistor, right, resistor minus VR equals 0. And so this holds true for any closed loop, right, so it has to start and end at the same point in the circuit, and it can only go through each component once. Like if I had something like this, right, you then have two loops. And you go around either of these loops, and we'll not get into it now. It's not essential to have a deep understanding of this. We'll get to why I'm going over this in a minute. Because we know that these voltages add up to 0, so this is a source and this is a drop, we can then rewrite this as V equals VR, right? Because by just taking this over that side, adding VR to both sides, however you want to think of it. And so this kind of intuitively should make sense to you, because we've got this voltage here, and it's all dropped across this resistor here because there's nothing else to drop it across. So if there were two resistors here, we'd have to rewrite this as V minus VR1 minus VR2 equals 0. And then we could rewrite this again by taking both of these negatives over to this side. This voltage source is equal to the voltage drop across the first resistor plus the voltage drop across the second resistor. So it's just conservation of energy, really. If you've got this much voltage, however much it is, it all has to be dropped. You can't have any left when you get back to the negative terminal, which makes sense, because this is, you know, if you're saying this is your ground, you get to pick ground, then this is at 0 volts. So you can't have any more voltage left there, and you can't drop any more voltage across these components than you have available at this source, because where does that voltage come from? If you can't get voltage from thin air. And so this is actually telling us a couple of things as well. So now if we go over here to Ohm's law, we can substitute Ohm's law in. So we had this to begin with, and we can substitute this in, right? So we know that the current is the same the current in a series circuit is the same at every point. So we know the current through both of these resistors is the same. The only unknown we have, or the only variable we have, is a better way to put it, are these R's. So let's, instead of writing this, we can write V equals I times R1 plus I times R2. Right, and then because we have I's multiplied by both things, we can take the I outside, and we can just say I multiplied by R1 plus R2. And then we can divide both sides by I to get the I over this side, right? So imagine that was that divided by that, because if you divide both sides by the same thing, you're allowed to do that. And so you've got V over I equals R1 plus R2. And if we look over here again, V over I equals R. So that's how you work out the total resistance. Right, because you can replace this V over I with this R. So the total voltage divided by the total current gives you the total resistance. And that's equal to R1 plus R2. So in a series circuit, and I'll write this up here, in a series circuit, we know that the currents are the same. Right, I1 equals I2 if there's an I. Right, these are all the same. This is I total, I1, I2, they're all the same. And the voltages, the two voltage drops added together, I've written minus there, I should have written a plus. Let's just put V1 plus V2. Right, and that will be V1, V2. Okay, and then their resistances are just added together, like we see here. Cool, so now, given any series circuit, by taking these equations or by doing your KVL loop and plugging in Ohm's law where you need to, you can work out any combination of any things. If you need to, so you can find the total resistance, and then you can divide that the voltage by that resistance, and that will give you the total current. And then you know the total current is the same in every component, so then you can multiply the total current by each individual resistance to get each individual voltage drop. And that's how it all works. Right, so we've got two resistors in parallel. We know they're in parallel because the top and the bottom are connected together. It can sometimes be a bit tricky to tell, especially when you first start looking at things. How is that connected in parallel? It can be a bit confusing at first. So the top and the bottom connected together, and they're in parallel. We know that these two can combine some way to give you a total resistance, and that resistance will be equivalent to the total current coming in. So we've got V here, we've got some current coming in here, and so we know there's going to be an I2 here, because this is R2, and an I1 here. And so what this KCL is saying, Kirchhoff's current law, is that the current going into this is equal to the current coming out. So these two currents, when you add them together, are equal to this. Or I'll write it down similarly to how I wrote it down before. Right, I tote. And then we minus the other current, so we've got minus I1 minus I2 equals 0. So then we got, right, and if there were more currents, you do the same thing, I3 plus I4 plus I5. Okay, and that's our first rule. So let's write down another one of these for parallel. So what about the voltage drops? Well, let's go back to our good old KVL, talking about voltages. Let's apply KVL. So now it needs to be a loop, right? So where's the loop? Is this the loop? Well, this is a loop, but it's not going to tell us much useful because there's no voltage sources in there. So the voltage drops around this have to equal 0, but there's no sources, so it will just be 0 plus 0 equals 0. Great. So it becomes a bit more obvious if I draw the power supply in. So now it's a bit more obvious. Remember how I said you can only go through each component once? So there's two loops. There's this one that goes down here, and there's this one that goes down here. And so I don't think I need to write it all out. We've got these are equal and these are equal. So that means these two both have the same voltage dropped across them because they're both just equal to the source. And that's true of all resistors in parallel, is that the voltages are the same. So we've got, I'll just write that straight down, V2. So you can see that that's the opposite. The currents are inverted, so they're equal, they're plussed. The voltages are inverted, they're plussed, and they're equal. And so now, if we want to work out the resistances, well, we just bang Ohm's law in again. Nice and easy. We need to get R in there somehow, because we're looking for the resistance. So let's divide this through by I to get R, divide through by to get I equals V over R, right? Because we've got the thing that we know and the thing that we're looking for on the other side. So we can take this, that's going to be V total over R total equals V1 over R1 plus V2 over R2, and if there were more it would be plus Vn over Rn for as many as you have. But all these voltages are the same on both sides. This, if it was say 10 volts, that'd be 10, 10, 10, 10. So we can just divide the whole thing through by 10, or divide the whole thing through by V tote. Because remember, V1 equals V tote, V2 equals V tote. So let's just get rid of this. Anything divided by itself is 1. And that's how you find the resistances. Now for parallel resistors, for 2 parallel resistors, but only for 2, you can say that the total resistance is R1 times R2 divided by R1 plus R2. So that was a really speedy, as fast as I can, through series and parallel circuits. We know these 3 laws now. We know how to find anything that we want in a series or a parallel circuit when it's to do with resistors. So let's very quickly go over a super simple series circuit that you've probably seen a million times. If you've watched any of these videos without realising it, you've seen it a million times already. Right, we've got 2 resistors. And as we said, we saw this before, we can calculate the voltage drop across either resistor by knowing the ratio between the 2 resistors. That is going to be the same ratio, because they've got the same current, V equals IR. So if you change the resistance, the current doesn't change, but so the voltage has to change. So it doesn't matter what the values of the resistor are, only you want to be careful not to draw too much current, because they can only take so much. Your power supply can probably only deliver so much. So let's say if this was a 9 volt and we wanted 6 volts here, then we just make this 2 times whatever this one is. So if that was 1 ohms, we'd make that 2 ohms. That was 100 ohms, we make that 200 ohms. Right, you see? And then we're going to get 3 volts dropped across here, and 6 volts dropped across here. Right, and this is called a voltage divider. And that's how a potentiometer works. You have the strip of resistive material and the wiper acts like this, and it's changing the ratios of these 2 resistors. So the overall resistance of the potentiometer never changes, only the ratio of resistance on either side of the wiper as it wipes around changes. And then if you take, this is the thing connected to the wiper and this is the thing connected to one side, and so depending on which side you take, you get a different voltage. And how does that relate to what we actually want to talk about, which is our filter? Well, if I draw a filter down here, right, you can see now that this is just that. It's just drawn funny. If you move that there and you replace this with this capacitor, boom, you've got yourself a filter. And so, how come this just does a voltage division, but if you put a capacitor in there, it becomes a filter magically? Well, the reason has something to do with probably the most misunderstood thing in all of audio electronics that we're going to talk about now: impedance. So, impedance, what is it? Well, to talk about impedance, let's think about what is a resistance. The resistance is the amount of opposition an electrical component gives to any given voltage. So a voltage is a force, the resistance is kind of opposing that force, and the current is what is allowed to flow by that interplay. So resistors, they don't care about what's coming in. If it's AC, DC, whatever, they don't mind. Whereas capacitors and inductors have a thing called reactance. Right, and the reactance for a capacitor is written XC, and inductors, we'll rarely talk about inductors because to get frequencies that are in the audio range using inductors, you need really huge inductors that are expensive and take up loads of space, so I'll only briefly talk about inductors, but don't worry about them for now. So you've got the capacitive reactance and your inductive reactance, and then just your resistance. Okay, so we've already spoken about resistance. So resistance just is. Resistance is just the stated resistor value, you know, written on the resistor, whereas your capacitive reactance and your inductive reactance, they care not only on, they obey Ohm's law, this reactance obeys Ohm's law, but the reactance itself, the resistance, the impedance, varies with frequency. So for a capacitor, it varies inversely with frequency. Right, so it's 2 pi times the frequency times the capacitance. And for an inductor, right, inductance is written as L, because I for inductance is already current. So capacitance is 1 over this relationship. Obviously for any given capacitor, this is a constant. C, the capacitance, is a constant. It's not going to change. So instead of looking at this kind of scary thing, with all this maths, let's just think about how it varies with frequency and think about how that's going to affect this voltage divider. Okay, so essentially, like I said before, impedance is a way of talking about the reactance of either a capacitor or an inductor and the resistance of a resistive material in the same kind of context, right? So you're just ignoring all of the other behaviours of it and only focusing on the characteristics that look like a resistor. And so impedance, I don't want to get too much into it, but basically impedance, you write it as a Z, and if you were adding them all together, like if you wanted to find the total impedance of this, you'd find this reactance, right, and you'd square it, and you'd add it to the resistance squared, and then you'd take the square root of that whole thing, and we'll maybe go into that in another episode. Don't worry about that if you don't follow that. I just thought I'd include that for completeness. We're not going to be doing anything like that. We're going to try and analyse this without doing any maths at all. We're just going to look at it and we're going to think about this relationship, and that's going to inform what we're going to do. Let's call this V out, and this is going to be V in. So we said before, the ratio of these two impedances is going to determine how much voltage is dropped across this part and how much voltage is dropped across this part. And so we know the ratio is inversely proportional to the frequency. So as the frequency goes up, this reactance is going to drop. Right, so I'm going to draw a little crappy graph over here. This is impedance, or rather capacitive reactance, which is for this, just this on its own, just equivalent to the impedance. I'm not going into the maths of it. So when the frequency gets very, very high, this number gets smaller and smaller and smaller. So as we go up, we're going to trail off, and at some very high frequency, we'll be basically at 0. And the opposite is true for a very low frequency. If this is very low, you know, 1 over approaching 0 gets huge and approaches infinity. So let's just say for the purposes of this that some very low number that approximates 0 Hertz has some very large impedance that approximates infinity. So at a very low frequency, we have a very high impedance. At a very high frequency, we have a very low impedance. And so, this is what that graph is going to look like. So what we can say now is as the frequency increases, this impedance is going to drop, and V out is going to approach 0 as all of the voltage is going to get dropped across here. And at lower frequencies, the opposite is going to happen. This impedance is going to get very, very high, and so the ratio of these two impedances is going to favour this. So V out is going to look like V in. And this is how we have filtering, because at higher frequencies, so if you imagine this was a sine wave that just slowly increased in frequency, at the start the output would just look like that low frequency sine wave, but as the frequency goes up and up and up, the amplitude is going to go down and down and down until you can't hear it anymore. And so this is called a low pass filter because it allows low frequencies to go through. If we took the output across here, or if we flip these components around, we'd get a high pass filter and it would look the opposite. And we would have a curve that looks something like this. Right, very roughly, and it's going to be a low impedance at low frequencies and a high impedance. HPF is a high pass filter, and LPF is a low pass filter. Right, so in this circuit, I've drawn this diagram very badly, but so there's this point here. If these are the same value, regardless of where we had them, and this point here is the 3 dB point. Right, and that 3 dB point is where the output has dropped by 3 decibels compared to the input. And that's how we describe the cutoff frequency of a filter. The frequency of the 3 dB point is given by the equation 1 over 2 pi, remember this, RC. So if we want a filter that gives us a certain frequency, we pick our capacitance, right, and then we can rearrange this equation. So we've got this equation here, just divide through by F, multiply through by R, we'll swap these two around. So you pick your capacitor, you pick your frequency, and you got your resistor value. Easy. And so another thing that this is telling us is that, right, if we make this a variable resistor, what we can do is by varying the resistance, we can vary the 3 dB point, which is going to vary the cutoff of the filter. And that's how we get a filter that we can control and move with audio. And once we've got that, we can put this in our feedback path, and like we were doing before, we can electronically control this filter with resistances. We can do you can either do the routing thing to have an 8-step filter that steps through, or we can move on, which we will do soon, to some more advanced control techniques. So this is a low pass filter. That's the very basics of circuits with resistors and filters and throwing everything in there. I thought I'd just do it and get it all out of the way so that I can just refer you to this video every time I bring something like this up. So if you forget, you can come back. We've got everything written down here. We've gone over impedance and blah blah blah. We've gone over, it's all been very brief, but we'll go over it more and more and more. You know, this is the type of thing that you need to kind of go over and see lots of examples, and then one day it'll just click and it'll be easy. So come back next time. We're going to build these filters up. We're going to do some active filtering, because obviously as you filter, you can see the gain goes down. So you want some type of circuitry that can turn the gain up, so that when you've got a filtered signal, it still sounds as loud as it did before. Otherwise you're constantly mucking around trying to get a decent sounding sound, which we don't want to do. So I'll see you next time.